Let's go ahead and get started. Welcome back to Zoom school as unexpected weather pushing us virtually again here today. I think it's fine. I mean, either way, we record it and you can always review content afterwards. Where we left off on Tuesday is we were working through, I guess I would call it the pencil and paper elementary approach to doing line rasterization. And afterwards, office hours, someone talked to me and said, "Well, why are we talking about lines, whereas in the lab we're only doing triangles?" It's really the same kind of approach. So we can take this line rasterization approach and generalize it to the triangle case. That is not the only way to do the triangle rasterization. There are other approaches that use a different kind of coordinate system. So if you see the term barycentric coordinates, that is a complementary but kind of different approach. But this approach, where we are rasterizing lines and we really do just treat our triangle as an intersection of three lines, um, allows us to take this approach and sort of directly apply it. And you'll start to see as we go from the kind of pencil and paper, just calculating based on line equation approach to this Bressenham's approach, that is effectively what we are doing in our MP2 lab. Let me also add that the main design criteria that may seem a little quaint to us now, but is very relevant certainly in the time that this was invented, as well as for our own limited hardware platform. The reason we are not just taking this approach of calculate the line equation, plug X values into it or Y values into it, as this case may be, and go from there, is just the extra computational hardware required of doing that. Primarily, I would say, as a first design criteria, we want to minimize or completely eliminate the amount of division operations and hardware dividers required. And as then a secondary criteria, can we also start to not eliminate necessarily, but minimize the number of multipliers required? You think back to your CPRE 381 days, um, those multipliers and certainly those dividers are maybe more quadratic in nature in terms of like the amount of transistors, the amount of chip real estate, the amount of time associated with design and test and integration of those. There's something if we can avoid, if algorithmically we can modify what we're doing, if we can avoid, there's definite benefits in terms of the underlying efficiency of the hardware, potentially the speed of the hardware. So you see a lot of this in graphics algorithms, although this is slowly changing over time. Can we do something that, in terms of the algebraic representation of what we're trying to do, is a relatively straightforward thing? Can we manipulate the math in such a way so that we are doing less of the divisions and multiplications that otherwise would take up a good chunk of our chip real estate? That was the case when these algorithms were invented. We're talking 1960s, 1970s era for some of these algorithms. It's still the case for us today that even if we have enough chip real estate, there's still benefits if we can get the same performance back out without having to dedicate all that chip real estate to doing things like division and multiplication, or to limit the amount of both that we have here. Um, there's still benefits in doing so, and so that's why we talk about Bressenhand's line rasterization algorithm. We refer to the one we are doing in lab as Steffen's rasterization algorithm. Mike Steffen was a graduate student here a number of years ago. He's sort of a director at AMD and their GPU architecture team now. And it was the same kind of philosophy. What can we do to minimize the amount of, outside of some perhaps initial per triangle setup, the amount of arithmetic in terms of multiplications and divisions we have to do after the fact? So that's why we're talking about what is otherwise mathematically a very straightforward thing we're doing here. Here's a line equation, slope intercept form, just follow it and be done. Here's the motivation for why we have Bressenham's line algorithm, in the first place, and why we ourselves have our own complicated line algorithm and triangle algorithm in the first place. So we left off. We were talking about slopes, and I wanted to also just kind of reiterate that we are thinking about this kind of x y plane and turning things on and turning things off in terms of our pixels here. That slope and this discussion of whether we want to solve for y as a function of x or x as a function of y applies to our coordinate plane here, but applies to all of our attributes as well. You can think of your green channel as having that slope, and it's the same concept here. So how our green changes as we go from left to right or from top to bottom for our particular line or our triangle is still very relevant here. Effectively, in our rasterization algorithms, we treat all our attributes as the same. They have a starting point, starting value, they have an end value, so they have some sort of slope or some gradient associated with them. And our job is basically just to calculate the interpolation from start point to end point, which we can always do via that slope intercept equation of the line for green or for x, y, or z, or for any attribute. But now we can look at Bressenham's line algorithm as how do we do so without that additional mathematical steps along the way. And we can think of it in terms of the discrete nature of what we are doing here. As we move across our x-axis, we're moving in unit intervals. At this point, we're doing rasterization, and we're doing rasterization in the so-called screen coordinates here. It's post-viewport transformation. So presumably we have these vertices, they've been transformed, the triangles have been stretched or rotated and things like that. But the end result of our coordinates is in the screen coordinates, where the values themselves may not be integers necessarily, but they're corresponding to an integer space, meaning we have a 1920 by 1080 resolution of our window or viewport we're wanting to render to, and so our x and y values would be in that rough range, whether it's 512.5 or 32.0, it's in that integer effective range of our screen resolution here. So we have our x-axis and our y-axis, and as we're moving across in our unit intervals on the x-axis, this whole idea of the Bressenham's rasterization algorithm is we don't really need to calculate what the value of y is at any given x location here. As we go from x sub k to the next one, x sub k plus 1, we're really actually making a decision. We're just choosing between the two different y coordinates. Another way to think about that is, again, assuming our slope is between 0 and 1 here, and we can always rasterize and guarantee that that's the case. Assuming that slope is within that range, we're either deciding just to continue to the right or to the up and to the right. And that's what's being visualized here on the slide, that no matter what our equation is, assuming our slope fits within this range here, we are determining from x sub k to x sub k plus 1 as we've moved one unit over in the x. Do we want to go to this location or do we want to go to this location? And that can be generalized to our green, red, blue channels as well. We generally, if we want to worry about maybe the accuracy of what we have going on here, we want to select the point of these two that's going to be closest to that line of those two. Another way to think about that then is we don't necessarily have to calculate what that actual y sub k value would be in practice as we apply the slope intercept form of the line equation. We just need to figure out which one is closer. So in terms of this rasterization algorithm, that's kind of what we're attempting to do here. So at that position x sub k plus 1, we actually care not so much about what the actual value is going to be of y at xk plus 1. We care about what that distance is going to be. How close are we for the so-called correct value of y? How close are we to the pixel that's one unit step above where we're currently at? And how far away are we? What's our distance to the pixel that would be at the current value of y that we are currently at? That vertical separation. We can just label the one d upper for how far away that is, the other one d lower, and then our decision ultimately becomes which one is smaller. If d upper is smaller than d lower, we should be filling in that uppermost pixel. I guess you can kind of see that in the previous one, although it's a little bit of a closer call than I would otherwise like. We have a value of d upper we could calculate for here. We have a value of d lower we could calculate for here. And we can see that d upper, you can kind of squint and see it is smaller than d upper. We should, for this example one, we should be filling in this pixel for this one. Because it's smaller, it's closer, it's the more accurate. If we were to do the rounding approach that we were doing previously on Tuesday, we would round up in that case. So we're rounding without actually calculating the rounding here. We label that one region d upper, the other region d lower, and we can actually just algebraically calculate what that corresponds to. D upper is the distance between the correct value of y and what that y sub k would be, as is d lower, right? D lower is the one that's below the line, so d lower is the value on the actual line minus y sub k. D upper is the value above the line, so it's actually yk plus 1, because we're going up 1 unit step, minus that value of y there. And we can just plug back into the line equation to get what that works out to be. D lower is then equal to m times xk plus 1 plus b minus y sub k. Likewise for D upper, it's y sub k plus 1 minus the value of that equation calculated for y. That doesn't really fix anything as of yet. So just looking at that formulation of it, that doesn't actually tell us anything in terms of, okay, we've saved some arithmetic here. So bear with me for a couple more seconds. We don't actually, although we have the equations here for D upper and D lower, we don't actually care about the value of D lower and D upper, right? We don't care that one is 0.2 and the other one is 0.8. We just care about which one is bigger than the other, right? We care about, are we closer to the lower point or are we closer to the upper point? So consequently, as opposed to actually worrying about calculating D lower and D upper, we can just calculate the difference between them. And there's a version of this that would do D upper minus D lower, but it's the same concept here. Instead of calculating D lower and calculating D upper, and again, you may just have to go back to the slide and kind of trust the basic algebra here, we can just calculate D lower minus D upper here. That allows us to do a little bit of factoring here that kind of simplifies the math a little bit. So D lower minus D upper doesn't look too much better yet. We still have that that value for the slope there that would require a division. But again, we don't really care about what D lower is. We don't really care about what D upper is. We care about which one is bigger, right? And so any transformation we apply that keeps the sign of that calculation the same is still going to be valid for our purposes of determining, should we go up or should we stay with the lower pixel that we have here. So while we can calculate D lower minus D upper, we really just care about the sign of it. So we can do a little bit of algebraic hand waving here and say, well, we have that m value, which is the real problematic value that we have here. If we multiply both sides by delta x, that gets rid of the m, right? Because m is just delta y divided by delta x. We just factor everything through with delta x along the way, and a little bit of algebra along the way here gets us a term that at first blush isn't too bad. We have the value of x sub k, we have the value of y sub k, we're keeping track of delta y, delta x, and then there's some additional constant terms here that are related to the line equation itself that we can just kind of simplify and for now just call c. Again, this is a value that is not directly related to the distance calculation itself, but at least would have the same sign as that calculation of D lower minus D upper. That's all we really need to know. Is it positive? Is it negative? We make our decision based on that calculation. That is the same math on this next slide here, but now we're just referring to it as a decision parameter here. Let's erase this thing here. Maybe it's only on my screen. Okay, there we go. Erased. Nope. 1 second. Well, if our value for this decision parameter is going to be negative, we're going to choose the lower pixel, right? And we're going to choose the lower pixel because in that case, D lower is less than D upper. Maybe it's a little bit of a double negative in terms of how we're thinking about it, but that's what's happening here, right? D lower, if it's less than D upper, we want D lower. It's closer to the lower pixel than to the upper pixel. Otherwise, if it's positive, that means D lower was greater than D upper. We want to choose the upper pixel there. So this is still seemingly requiring a decent amount of math. We're not quite done here, but we can start to see that as opposed to calculating a full line equation, what we have here isn't too bad, right? What we have here is just an equation that gives us this so-called decision parameter, right? That says, here is, for a given step, a value that doesn't mathematically correspond directly to the line equation anymore, doesn't require any division at least here, although we see some multiplications and some additions here, but at the very least tells us, is it positive? Is it negative? Consequently, we go up or we don't, or we just go over. And we each step along the way, we're making that decision. Do we go over or do we go up? We can even simplify this further though, right? If we think about our line equation, we can recognize that we're going from left to right. And we're making these changes in the x dimension in these kind of unit steps here. So while for any individual point in time, if we were to calculate this decision function, we have to do all that math. As we go from p sub 0 to p sub 1 to p sub 2, as we go from step to step to step, a lot of those things don't really change, right? Because we're just incrementing our x value by 1 each time. Let's do just a little tiny bit more algebra and see what that would correspond to, right? As we are changing along in the x-axis here, you can just do everything with those integer calculations. So for p of k plus 1, it's the same equation plugged in here. We really care about how much that decision parameter is going to change. So from p of k, p sub k to p sub k plus 1, if we just subtract those two here, what we have is a very small amount of change as we go here, right? X sub k plus 1 minus x sub k, that is always going to be equal to 1. So we would be adding 2 delta y each time along the way. If we wound up going from the lower up to the upper, if we wound up going upward 1, we would then be also subtracting 2 delta x. But if we kept ourselves horizontal along the line, we would not be going up as well. So each step along the way, we're determining, do we add 2 delta y or do we add 2 delta y minus 2 delta x? So as I just mentioned, that as x of k plus 1 is the same as x of k plus 1 because we've gone up by 1 each time, we can calculate given our initial decision function here. Again, ultimately, really the sign of it is what we care about, but given our initial p sub 0, we can calculate p sub 1 by adding that additional term here, 2 delta y, potentially minus 2 delta x, because this y sub k plus 1 minus y sub k is either going to be 0 or 1, depending on what the sign is. If we moved up, then we do have a value of 1 here. If we didn't move up, then we just have a value of 0 here, and consequently, we're just adding the 2 delta y along the way. Going back to our initial value of p sub 0, it's just 2 delta y minus our delta x. You can go back to the algebraic formulation and kind of take my word for that. I think is probably sufficient. But we can now kind of plug and play and give this a try ourselves here, right? Where we can say, given our value of a line, so we still need our 2 points. We need to know what our delta y and our delta x is going to be. That doesn't require multiplication. That's just a simple subtraction to calculate that, right? We then would then have to calculate this initial value of p sub 0 of 2 delta y minus delta x. And then separately, we want to keep track of 2 delta y minus 2 delta x. All of that can be done without multiplication, right? As you've probably seen as you're implementing your MP2, when you're multiplying something by 2 or dividing by 2 for integer formulation of those values, you just are shifting. And so or fixed point representation for those values, you're just shifting. So we can get our delta y, we can get our delta x, and each step along the way as we're rasterizing, we just have to determine, do we go up or do we just go over? And we calculate p each step along the way, either adding 2 delta y minus 2 delta x or just adding 2 delta y. Each step, we calculate that value of p, we keep track of it because we need the prior value to calculate the next value, but our decision is then based on, if we go back again to this formulation, this whole point of this value of p is to determine the sign of it because it's related to the value of d lower minus d upper. So for negative values, we choose the lower pixel. Otherwise, we choose the upper pixel. Let's give it a try together. I'll walk us through the majority of the steps here, but I'd like you to try to follow along and try your own pencil and paper approach, and hopefully you come up with the same result that we come up with here. Again, the end result is not going to be a different looking line or a different looking triangle. We're still using the same line equation here, or triangle equations as we apply it to that. What we are doing here is basically just manipulating the algebra. And this is the kind of genius of this idea, so that we're not actually having to either even calculate the slope of the equation in the first place, or plug in values of x for y and do the calculation and the rounding and everything that would have required us to do kind of the naive rasterization approach, which mathematically is correct, but just requires more arithmetic units and more computation than what this approach is going to require. This approach requires some initial setup. So given a points in screen space, and here we have 20, 10 and 30, 18 here, we have to do a little bit of setup. We don't have to calculate the slope, but we do need to know our delta x and our delta y, and consequently our 2 delta x and 2 delta y. But that's just subtraction. So delta x is 10, delta y is 8. We then can calculate our initial value for 2 delta y minus delta x. That's our initial p sub 0 parameter. That's our initial decision parameter. and that value is going to be 6 here. So we're going to start with where we determine the sign of that decision parameter, and that lets us determine whether we should go up or down. And, until you've done it a couple of times, I think it's relatively easy to get it kind of backwards, but D lower minus D upper. So if we get a positive value for that sign, that means D lower was greater than D upper. So we start with this value of P sub 0 for this line. The sign of it is positive. D lower is greater than D upper, not by 6, but it's got the same sign as this decision parameter here. D lower is greater than D upper. The distance to the lower point is larger than the distance to the upper point. We should go up. We should go up a point then correspondingly, um, because we're closer to that upper point. So let's give it a try here. So again, this is a very just fast incremental algorithm for doing this interpolation here, and it allows us to calculate it step by step after that initial setup, doing very simple math along the way. So we had for our value of k equals 0 for that first step, we have our value of p sub k. That value is going to be 6. You might take my word for it. And then our next value for x of k plus 1, y of k plus 1 is going to be 21, because we're always going to be going up in the x dimension. And for a y, we're going to be going up 1. We can kind of fill in, although you can kind of see it here as well enough. We're going to kind of fill in this is my attempt to fill it in. We have our pixel for this one right here. Okay, so we have our current value of p sub 0. From our value of p sub 0, we have to calculate what our next value of p sub 1 is going to be. P sub k plus 1 is given as the equation here, right? We have our initial value. P sub 1 is going to be equal to that value of 6 plus 2 delta y minus 2 delta x, right? Because here we did go up. So we're kind of building up that distance to the upper pixel. And eventually the sign of this value, as we keep subtracting 2 delta x's, is going to eventually turn negative. So we have 6 plus 2 delta y minus 2 delta x, and we have it even given here for us of 2 delta y minus 2 delta x is negative 4. It's nice that I already calculated that for you. So from our value of p sub 0 equals 6, what is our value of p sub 1 going to be? Someone tell me in the chat, or you can speak up. Chat might be easiest. It's up to you. Initial value of 6. We went up 1. So we take the 2. Yep. So we take the value of 2 delta y minus 2 delta x, which is negative 4. So our value of p sub k plus 1, or p sub 1 in our case here, is equal to 6 plus 2 delta y minus 2 delta x. So it's 6 plus negative 4. Ben, I think you've got it. Six plus negative 4. We can do that one in our head. Thank you, Andrew. You got it. That's going to be a value of 2. Another way to think about that is, we're going upwards each step along the way here. That previous pixel got erased a little bit. There it is again. We're still positive, although we can see we're getting a little bit closer to being negative here. We're still positive, so we're still going up 1 here. And we just do it again. We can write down the line. The next point would be, it's 2212. We do it again. We add that 2 delta y minus 2 delta x value. We can just assume, we can maybe just keep track of it. It's either going to go up by 16 or it's going to go up by negative 4. If I keep it here, you can kind of keep track of it as we go. that if it were a positive number, we go by -4, or we decrement by 4. If it's a negative number, we go up by 16. So we're building that sort of positive credit for the upper part of the line, and then eventually we flip the sign entirely, and then we continue to drop it as we go. So the next point is p sub 1 is going to be equal to 2. The next subpoint here, we've added another -4, so our value is going to be -2, and our next point is now going to be 2312 again. Because now the sign of that decision parameter is negative. That means d sub upper was greater than d sub lower. We're closer to the lower pixel than we are to the upper pixel. So we've finally kind of flipped the sign of our value here. Now y sub k plus 1 minus y sub k is equal to 0 in this case. So consequently, we are adding just 2 delta y. We're going to add 16 to it. We can kind of see where it's going to go here. So 14, which is going to give us going up another pixel. Then it's going to be 10, still positive. We go up another pixel. And you can see where we're going here. 6, 2. We go up 2 more pixels. And it should work out that it gets back to our original line segment here. Then we're back to -2. So we stay at that same location. That's 28, 16, because we still move over in the x dimension here. Then we go back up to 14. And then we have 10. So the answer should be, the final one should be our original point, 30, 18. I'm not going to fill in the individual pixels on the line here. You can kind of squint and see where they're going to be. And we know whether yk plus 1 minus y sub k is 1 or 0. It's not if the previous term is greater, it's whether we moved up or down 1. So y sub k, we don't know what y sub k plus 1 is until we've calculated it. So y sub k plus 1 in this case is 12. Y sub k is 11 here. So we're either going over 1, just to the right, in which case the difference is 0, or we're going up 1, in which case the distance is 1 between the two of them. So in this case, if we wanted to kind of write it down here, the reason we are moving over as a factor of 1 is because that delta, or y sub k plus 1 minus y sub k, is equal to 1. We've moved over 1 here, but here it's equal to 0. Now again, here it's equal to 1. Apologies for the handwriting. Equal to 1, etc. Yep, based on the prior steps, change along the way. Did we previously go up or not? How much closer are we now to the original line, depending on whether we went up, chose D upper, or we chose D lower along the way? Yeah, the way that's phrased here with regards to p sub k plus 1 is the decision we make at step k plus 1, and uh, depending on what the sign of the prior p sub k is, the value is either going to be 0 or 1. I see what you're saying. You could write that as y sub k minus y sub k minus 1 if you wanted to. Um, there's a little bit of semantics there about the value of k. Well, this is point 0, but then there's the decision that we're making at point 0 here. um, so there's an initial step where we just calculate that value of this without any, there is no prior point we have here, right? So there's the initialization value for p sub 0 gets us 6. Now when we've calculated the next value of p sub k is equal to 2, now we know that the difference between the two of them was 1, right? Because we went up 1. So you could argue we could have phrased that as y sub k minus y sub k minus 1, but it's the decision that we're making at point k equals 0, 1, 2, 3, etc. along the way. So we have to use the prior point to know, did we go up 1 or just over for that prior decision. You don't know it yet, right? Right. So it's the did we go up 1 or not? Then we add that 2 delta, a negative 2 delta x, or not along the way. Yeah, because I mean, it's here, but what's not really being shown is that initial point is a slightly different equation, right? So that initial decision parameter is not based on yk plus 1 or yk. We don't know yet. So we first figure out how close are we for the next point to the upper or the lower. And then from there, we can determine we went up 1. Now our calculation uses that 2 delta y minus 2 delta x for the next one. I completely understand, the crux of your question, right? Because it's a little the way I wrote it there is a little ambiguous. That what is k plus 1 and what is k. We don't know k plus 1 for the next point yet. We're deciding what the next k sub 1 is going to be. That's for the prior k and k plus 1. What was the value? That's a little ambiguous. This phrasing here, I would say, is correct. You could have just called this something else here, but yk plus 1 minus yk is either 0 or 1, depending on the sign of p sub k, depending on the prior or the current decision parameter. That sign determines whether this is a 0 or a 1. I could have written this as y sub k minus 1, and it would have been also maybe ambiguous, but would have also been, I think, correct. It's doing the same thing. In terms of actually filling our triangles now, one such approach is referred to as kind of the edge walking concept, in which we know we have our 3 vertices that comprises our triangle here. And now, given Bressenham's approach, we know how to rasterize the lines that make up those edges of the triangles. Um, Given P0 and P1, and then P1 and then P2, and then P2, and then back down to P0, we have 3 lines. So we can apply Bressenham's to all 3 of those lines, and then consequently, once we've done that, there presumably now is a set of points for each of those horizontal edges that we have here. That's why it's referred to as the edge walking approach. A little hard to see. I'm just going to kind of try to hover my mouse to show you what I'm getting at here. So assuming P0 and P1, and P1, P2, P2 back down to P0, that's 3 lines. I think we look at what we just did. We still have to kind of squint to see how that does the gradient for the other attributes, but we can fill in those pixels, I think, right? Applying that Bressenham's rasterization for line approach here. Now, in having done so, effectively now for each of our vertical edges here, as we go from y value here at 0 to y value here at point P1, and y value here for P0, y value for P2, each of those would then correspond to a pair of points on the same y coordinate, which we could then just treat as a line. We don't think of it as a line, but it is really a line, right? Maybe it's hard to see at the very top here, but we could look at maybe this row that we have here in our particular middle of the triangle, where we now know the value for this pixel, or this fragment. We now also know the value for this particular fragment, and we don't think of them as being, described as lines, but we could always draw a line between those two. We know what this value is for x, y, and attributes. We know what this value is for x, y, and attributes. We can take those 2 points, they have a slope, we can rasterize a line between them. So that's the edge walking approach, right? We do the outer lines, we basically build the edges of our polygon, and then we go row by row. And we rasterize the lines at each of those y coordinates at each scan line, and we do another Bressenham from left to right as we go. That doesn't necessarily entirely solve the question of how we do that rasterization, because we still have to determine how do we know that we're inside the triangle at any given point in time. This is where we start to get into that triangle test kind of module that's a little tricky for MP2 here. But the basic concept is basically the same. We can determine on a row by row basis how much we're changing in our delta x for our other attributes here. And we treat it as just now a series of horizontal lines that we're doing that rasterization for. We still have to know where our edges are, and we can do this very quickly, but then we still have to worry about some, for example, edge cases. First off, part of the issue is, as we have these viewpoint coordinates that we're working with, and now that we're not working with lines and we're working with triangles, we oftentimes are going to have some kind of tricky edge cases, no pun intended here, where how are we going to be dealing with where mathematically the edge of the triangle is, but then ultimately do we have a pixel that is turned on or turned off here? Modern systems don't solve this via this mechanism. The suggested mechanism that Bressenham would have provided would have said, just round consistently, or just make a consistent determination that left edges you rasterize a certain way and right edges you rasterize a different way. Nowadays, modern systems use some form of anti-aliasing, and we'll get to that probably next week, where for anti-aliasing, you kind of solve the problem by rasterizing to a higher resolution than you're actually going to display to. So in rasterizing to a higher resolution than what you're going to display to, um, you kind of solve the problem by recognizing that, well, I'm making this binary decision of pixel on, pixel off, but ultimately I get to do a kind of averaging of those two subpixels or multiple subpixels to get our final result here. But the Bressenham approach is still basically taking the line rasterization algorithm and then just walking line by line by line as we go vertically through our triangle. We still have to determine those edge equations to determine whether a potential point is inside that triangle or not. That's the triangle test module that I was talking about. We can still use our line equations for that purpose. The original formulation is to use the implicit equation of the line. There's other terms defined here where given 2 points x, y, x0, y0, x1, y1 that define a line here, we can have an implicit equation for that line, ax plus by plus c equals 0. Given any arbitrary point, we can plug it back then into that line equation and we get one of three results. Either the point is exactly on the line, and if it is, then ax plus by plus c equals 0. Or the value for ax plus by plus c is either going to be greater than 0 or less than 0. I put the terms above and below the line in kind of quotes here, and I'm using air quotes to describe it because above and below isn't really well defined when you're thinking about a space like this, and you have points that are not just horizontal or vertical lines here. But you can think of it as being divided into two half spaces in our Cartesian plane here, where we have the points that are actually on a particular line. We have points for which, when plugged into the equation, the value is greater than 0. So if we want to call that above the line, that's fine. And then we have points for which the opposite is true. That as we plug in ax plus by plus c, we get a value that is less than 0 when plugged into that particular line here. So in terms of our triangle, you can then define our triangle by the intersection of those three half planes. So for a particular line, we get split into two half spaces or half planes here, above the line, below the line. Our triangle then can be defined as the intersection of the three half spaces for which our evaluation of the line is whether it's greater than 0 or less than 0. Either way, it's having the same sign is how we would define that. That the intersection of the three planes for which the sign of all three of those line equations is going to be the same. Now, this is going to go back to what I was talking about briefly on Tuesday when we were talking about primitive assembly of clockwise versus counterclockwise. For our purposes, I think it's going to be sufficient to say we can do an area calculation based on the ordering of our vertices. That's going to give us a positive or negative area for that triangle. And we'd want to have the same exact sign of that result for determining whether a particular point is inside or outside of the triangle. For now, I think it's sufficient to say, given a clockwise formulation of these three vertices and the corresponding calculation of A, B, and C for the three lines that can be defining that triangle, we would want the value as we evaluate all three of those lines for points inside the triangle to be greater than 0, with the points of equal to 0 being on the triangle as well. But for the edge walking approach, we've already rasterized those points. We want to now, internal to the triangle, rasterize all the points for which the evaluation of all three edge equations is going to be greater than 0. This is another way of looking at the same exact concept, right? Which is we are calculating those line equations for all three of the lines. The pixels that we actually care about are those for which, for all three lines, we get a positive value for doing ax plus by plus c. We can limit our search space in terms of algorithmically which possible pixels we want to look at by just calculating a bounding box, and that should start to look similar to what you're already working with our triangle setup. That's that's technically an optimization. I guess you could look at all x and y coordinates and calculate the triangle equations or the line equations for the triangle based on any possible pixel. But I think we can look at that and say, given our values of x and y for all three of our points, there's a minimum x, a minimum y, and a maximum y. And that kind of sets the box, sets the rectangle for which we have to do our rasterization. And that limits the amount of things we actually have to check along the way here. So that requires a little bit more setup. So there's the setup required to do the rasterization for each individual line, and now the setup for the actual triangle equation here, which is still based on the component lines here, but requires a little bit more setup. So here now we're thinking about the implicit form of the equation for the three possible lines, and for A, B, and C for given 2 points X and Y. Now, you may or may not recall, you have um, three variables that we're trying to solve for here: A, B, and C, and kind of two data points and that we have here, two equations and three unknowns here. So there's infinitely many A, B, and C's, A's, B's, and C's for any pair of points here. There's a least common multiple version of A, B, and C. But for our perspective, again, we care about the sign of this calculation. We don't actually care about the value of a point. We don't care if it's 25 or 25 million. We care about whether it's going to be a positive value or a negative value, just like for the line rasterization equation here. So one way we can do this is we can solve for A and B in terms of C, and then pick an arbitrary C so that, again, the resulting math doesn't require as many multiplications and divisions as it otherwise would. And I keep harping on division and trying to avoid division. We don't talk that much about division, but we do have one in triangle setup, that there is still at least one division operation potentially required there. And I think you can see the difference, right? When I tell you that you need to do addition in your logic, synthesis tools are reasonably good, given an appropriate coding style, of inferring fast adders in your design. Likewise, although this wasn't always the case, and at least for FPGA technology that we're using, if you need a multiplication, an integer multiplication in your design, the tools are also pretty good at inferring that as well, right? A times B, you just use the little multiplication symbol. Um, the tools are pretty good at inferring that for you. Sometimes, if you need something really custom, that's not sufficient for you. But for a lot of our purposes, that is sufficient. You may have tried, or maybe not tried, to use like the division symbol to do some sort of division via hardware inference in Vivado. And if you tried that, I think you'd recognize it's not going to work very well at all. There just turns out that algorithmically, or at least the underlying hardware fabric that we're targeting, there isn't a design kind of independent coding style to infer dividers that meet whatever design criteria you may have. So it's not just a matter of the amount of transistors we're using or lookup tables we're using to do our division versus our multiplication versus our addition. Just the design complexity gets that much more as well. We have just a single divider in the design right now. Um, Getting it down to one division isn't that bad. We'll see here this also requires one division for our triangle. But even that one divider takes a decent amount of work. Later on, we'll see there's at least one additional divider we need in our system to be able to do the kind of viewing and transformations we're interested in. But we really do try to minimize the amount required there because it does add a lot of extra complexity to the design. That's something you definitely want to simulate as well. So I'm guessing most teams are already there, but given both your pre-lab calculations as well as kind of there's a little tiny web JavaScript app that shows the calculations in practice, you should at least be able to confirm in simulation, given these 3 points, my triangle parameters are correct, and that would only be the case if your division was correct as well. And the rest should just be debugging state machines. I know, easier said than done necessarily, but you should at least be able to get to that point very quickly and confirm that you're interfacing with that component correctly. The little pipeline structure that was kind of created for you for triangle setup is doing what it looks like it should be doing. And then now you're just debugging that traversal test kind of tight feedback loop here that we have. Going back to this version, this triangle setup, we have A, B, and C that we need to calculate given 2 points. we actually have arbitrary many possible solutions for A, B, and C here. We are going to want to set up A and B in terms of C, and we're going to do it such that we can minimize the math required. So, those of you who remember your linear algebra, this is a relatively straightforward one. We have ax0 plus by0 plus c equals equals 0. We can then formulate that to then define a b as a linear system, as a c as a function of a and b here. One way we can solve for a and b is then to calculate both sides by the matrix inverse here. So you can do your determinant x0 y1 minus x1 y0 to get our value for a and b as a function of c. This looks like a complicated amount of math here, and it potentially could be, but this is a and b as a function of c. Again, we don't care about the actual values of a, b, and c. We care about the sign of the line equation as we plug in points x and y, and we're going to see the same thing here. We're incrementing our x by 1. Our delta x is going to also be a constant in our system. In this case here, we don't care about c. We care about the sign of the line equation. We can just set c. We can set it to anything and solve for a and b. We can set c in this case to be equal to x0 y1 minus x1 y0, and then that all just kind of factors out. When we do that now, we get a is equal to y0 minus y1, and b is equal to x0 minus x1. Given 2 points, we can very quickly calculate a and b as well as c here in this case now. We can then calculate ax plus by plus c and determine the sign for each of those potential pixels we have along the way. But even then, we can do a little bit more optimization, and perhaps we can think about this from a software perspective. So there's that initial triangle setup. So we have to calculate the edge equations for our triangle. So the three A, B, and C pairs that we have here, the three A, B, and C values for first line, second line, and third line. We also have to calculate the bounding box as an optimization. I think you saw that that calculation isn't too bad. It's just checking for the three x values, which one's the smallest, which one's the largest. For the three y values, which one's the smallest, which one's the largest. And then you can think of our rasterization algorithm now as effectively being a double nested loop here, right? For our outer loop, we look for each scan line. That's our y loop in the bounding box. So for y equals y min, y is less than y max. Now for our inner loop, that'll be our x loop, checking each pixel in the scan line and then evaluating the edge equations and determining, are all values greater than 0 or not? If they are, set the next value for our pixel. If they aren't, continue on to the next one. For our purposes, when we're doing this in the lab, the extra part here is that set pixel function has to then still worry about the gradient for it, has to still do the rasterization for the green, the red, the blue, all the other channels. But logically, what we have here on the next slide, which is kind of a high level software view of what's happening in the system, is exactly the same as what you are implementing in your lab. Again, maybe it doesn't look this way because um, because we don't have these double nested for loops, and we are effectively going on a row by row basis. There's a couple more traversal hacks that the Stefan algorithm does that this one is not necessarily doing, but otherwise it's effectively the same. Couple more ways we could optimize this code here. First off, let's just make sure everyone understands what I'm talking about with this code. So we could call these two functions, we could call these setup triangle. In this case, it's slightly different. It's determine your bounding box. So set x min, x max, y min, y max. Determine all the values of a, b, and c given by this formulation here. A is y0 minus y1, b is x0 minus x1, c is that x0 y1 minus x1 y0. Calculate those values. So that does require some multiplication. That is a one-time calculation that you're doing per triangle here. And now basically scan through our bounding box is what's happening here. So for each value of y, consequently for each value of x, calculate, you can call that equation 0 or edge 0. Equation 0 is ax plus by plus z. Same for equation 1, for equation 2. We don't actually care about the value of E0, E1, and E2. We care about the sign of those. So one way we can look at that is just to say, if all three of them are greater than 0, that pixel is inside the triangle. So whatever is required now to generate the fragment, we do at that point. We set pixel. We have some other logic that is determining what our pixel needs to be for that value. Even thinking of this in the software formulation of it, we can make this a lot faster, at least in terms of the amount of math that this is doing, right? We're thinking about how do we minimize the amount of multipliers required? Perhaps how do we minimize the amount of iterations required for our traversal as well? The Stefan algorithm is a little bit complicated in terms of it's trying to do some quick optimizations to determine it's much easier to go, again, incrementally in the x direction, plus or minus one along the way, and it wants to end as quickly as possible. Whereas this code is written doesn't do any early termination at all. It's just do the entire bounding box. We could have done that as well. That would have been fine. But you can usually determine earlier than later when you can stop on any particular row. Likewise, this is mathematically correct, just like for pre-Bressenham rasterization, that was mathematically correct. We are calculating the value of the line equation each step along the way, but we may be able to recognize that there isn't as much math necessarily required here to get this to work correctly. I would like everyone who is still with me here today, or if you're watching the video after the fact, to pause the video right now would be fine. Take a couple minutes and think about what kind of optimizations would still be possible here. We're describing the optimizations as software optimizations, but even if this were a state machine, the same kind of optimizations would potentially still be possible. This is our edge walking code. How can we make it faster in terms of minimizing either the number of steps or the amount of math required in each particular step? I want you to take a couple minutes. So look at this. I can open it up in a code editor or something and we can kind of do the optimization that way. Let's take a couple minutes, think about it yourself. You can type some ideas in the chat, but wait a couple minutes before doing so. You could also speak up once I come back here in just a minute. And let's think about what kind of optimizations may be possible here. Okay. Any thoughts about how we can make this code faster? I um, just kind of copied it over to an attempt at a coding window here. Okay, first question. We're checking E0 before moving on to calculating E1, etc. Be an optimization. The answer is potentially. I wouldn't say that that's wrong necessarily at all. So if we can check E0 before we check E1, um, to have kind of like an early termination criteria, um, I think that's potentially the case. We could also check all the values, and if any of them are greater than zero, we could continue with the calculation. So yeah, so first thought would be, early checking termination. It's not that obvious to me, um, whether that would be faster or not, but that's one. Let's do it. So if E0 is greater than 0, this will require a little bit of refactoring. Or if E0 is less than or equal to 0, break, right? And we would do that for the other two cases. Now with a state machine, we're kind of going from state to state, but in this case, we're kind of early terminating that inner loop and saying, why even worry about E2 or excuse me, E1 if we realize that E0 is not correct? We don't really need to keep going. That is definitely one way to do it, and I think that's correct. Although with other optimizations, we might wind up breaking this, but for now, that's a valid optimization. Any other suggestions or thoughts? Absolutely. Now, if we were to do that, um, then this James's optimization, we probably couldn't do both. There's a slight issue because we'd have to keep track of which one is there. So there's nothing wrong with his optimization, James. Full points for that. I give you full credit for it. But this idea would be, we have this innermost X loop, but do we really need to calculate all that each time, right? Our value of y is not changing. Our value of c0 is not changing in this loop. What is changing is our value of that's fair. Our value of x along the way, and any arithmetic mistakes I make along the way are intentional. So catch me if I made one. But kind of winging this one as we go here. The idea that this is outside the loop now doesn't look like an optimization at first glance, but the first time through, and again, we're going kind of row by row. Now there's a sort of a row setup that's happening here. Here it could be thought of as the initial value for a given value of y for what that E0, E1, E2 value would need to be. Now when we want to calculate inside this loop what our value of E0, E1, E2 would need to be, we recognize that x started at x bin. X is only going to be incrementing by 1 each time, right? That's obviously what the x plus plus is doing here. So consequently, let's just comment this out versus kind of deleting it. We can just increment our value of E0, E1, E2 each time. Maybe there's an off by 1 error or something. If I have to check how I'm setting it. So because we're incrementing, we're setting it equal to x min. If we were to do it this way, we'd have to do the set pixel first. But that's fine. If E0, E1, E2, we would set it first, and based on just how I wrote it, we could have written it and set it up slightly differently. But it gives us the same kind of result here. Now we still have the same kind of like arithmetic outside the loop. We're doing all that calculation of the line, but the value of our line equation is only changing by a each step along the way. I like that optimization. I'm glad you like it as well, James. There's another optimization we can do here. It's a little backwards asking you to do this, but maybe think about the Steffens algorithm and how it's traversing. What optimization is that making to kind of minimize the amount of traversal it has to do? Well, one thing it's doing is it's realizing that as you're going into the triangle, as you're again doing this sequential raster scan on the x dimension here, once we go from outside the triangle to inside the triangle to back out again, we know we're done. It's a convex shape, so what that means is for us, once we're inside it and we go back out, we're not going back inside the shape at any given point. There's no holes inside it. There's no lines inside it that have any gaps inside them. So while we can do the whole bounding box, it's easier to think about this from the x dimension than the y dimension. While we can go through the whole bounding box, instead, as we go on a line by line basis, there's no harm, at least in this algorithm, in starting at x min. Stefan's algorithm starts at the prior ending point, which there's also advantages to doing that. But even starting at x min, we should be able to terminate this loop before we get to x max potentially. How would we do that? One way to reason about what we would be doing there would be to say some sort of code comment. If we were in the triangle and now aren't, we can be done. Something like that, right? We were inside the triangle. We now calculated we are not inside the triangle anymore. We can be done at that point. That would require some sort of variable. We can call it like x inside triangle. We would set to 0, right? So now when we do this calculation, let's add a little bit more logic as we're doing our set pixel here. If we're inside the triangle, so that same condition is still the case, E0 is greater than 0, E1 is greater than 0, E2 is greater than 0, we could do something like, we could just set it equal to 1. I don't think it matters what the value is. We could just increment it. We have something that is inside the triangle. Now, we weren't doing anything in the else case here, but we can now, right? Now we can say if we were inside the triangle and now we're no longer inside the triangle, we're done with that line. We were scanning points. At some point, x inside triangle was set to a positive value for that row, meaning we did get inside the triangle. So those values were true, or E1 is greater than 0, E0 is greater than 0, E2 is greater than 0. I like your idea, Ben. Make the code look more incomprehensible. But we were outside. At some point, we were inside. We are now outside again. That means we're done with the triangle, or we're done with that row in the triangle. We could write that in different ways, but if not x inside triangle, we're no longer inside the triangle. We're done. That's backwards. If we were previously inside the triangle, let's just be explicit. If we were inside the triangle previously for that row, and now we're not, E0, E1, and E2 are not, one of them is no longer greater than 0, we're done. We don't have to do anything else on that particular scan line. The Stefan algorithm is trying to be a little bit more clever because it's checking both directions. In this case, the optimization isn't quite as good because we're already starting at x min. So you could probably draw some really acute triangles for which this isn't that great of an optimization because we're always starting at x min, but it's really facing all the way to the right, and we're wasting a lot of time trying to get inside the triangle. And in Stefan's, you always have a likelihood of being inside the triangle as you go down one row because you're starting not at x min, you're starting at the prior x value that you finished off on. Again, for acute triangles, you're still not guaranteed to be inside the triangle as you go down one. I guess it's fair to say you're more likely to be inside the triangle when you start inside the triangle versus starting at x min for a particular triangle. That's the other small optimization that his approach, I'll call it our approach, is making. You go down one, you still have to check both directions. So there's both a x to the right and an x to the left. And that's where that traversal logic, I understand, can get a little bit complicated. There's just a few like double negatives along the way that you're trying to debug as you go. But it's basically this concept. This is only doing it for the one direction from left to right. His approach is doing it both left to right and then potentially right to left, and then consequently determining I was outside, I got inside, I'm now back outside. Same concept. I'm done with that particular row. I can now move down one particular row. which this doesn't look like it's moving down one row when we do this, but that's what that break statement's doing, right? Get us outside of this inner loop, go back to the y plus plus of the outer loop, and continue. That's the other optimization of the Stefan approach, where, again, in this case, we're calculating based on x min each time. But if you're at the prior x value, which we'd have to refactor this code quite a bit to get that to work. So I don't want us to do it, but I want us to understand that the equivalent traversal that you're working on for MP2, if we're not starting at x min, if we're starting at x prior, where we were the row before we are right now, we don't have to calculate this at all anymore, right? As we go down one, we just have to increment by b0 as opposed to calculating this line equation at all. So and you start with a known point. So you start at the beginning, the topmost vertex of the triangle. You don't have to calculate. You know the value at the topmost point. As you go to the left and right, you're doing this. You're just adding that particular x gradient dimension for each of our attributes. That's our C5, C6 values. Then when you go down one, you also don't need to do all of this recalculation. You're calculating what is effectively the y gradient for going down one in one y dimension there as well. So this is C code, so kind of pseudo code to kind of show what optimizations are possible. That's how we generally want to do our traversals as we go. What I want us to get to, although I think it could probably wait until after our demos on Tuesday, is what's happening after we do that initial rasterization. We've been assuming and working off the assumption that everything is fitting nicely within that viewport. And so consequently, any triangle we specify should be showing up on our screen. That assumption is true for the applications we've been working on so far, but generally that is not going to be the case. That we have, let's say, a game engine or some interactive scene. We have a camera that's going to be looking at a particular part of all of our geometry. And for the rest of the geometry, we're still potentially specifying it. We're still potentially sending those vertices down the pipeline, but we want to make sure they don't actually show up on the screen at the end of the day. You can think of that as work removal, clipping, culling, hidden surface removal. We'll start talking about some of those algorithms starting next week on Tuesday. Even though you're not working on those in the lab as of yet, we will be getting to some of those in the lab, and a couple of them could also make potentially good project ideas for this course. Let's leave things here for today. Everyone stay safe on the slippery roads and sidewalks and things like that. And I'm really looking forward to seeing some cool triangle related demos on Tuesday. Thanks.